Hi, my name is Kieran. I'm a master's student and I'm interested in mining and the applications of geophysics.
Hi, I'm Kassidy. I am an undergraduate right now, and I'm interested in field surveys and field work. In April, I am an undergraduate as well, and I'm interested in planetary geophysics.
Hi, I'm Dawn. I'm also an undergraduate in geophysics. I'm more interested in hydrology.
So we're going to be talking to you guys about geophysics, and if you couldn't tell already, geophysics has two main parts, geo and physics. So geo meaning earth and rocks, and physics being the study of systems and how they interact. So we're exploring the interior of the earth using non-invasive sensing methods, which my teammates will talk to you about now.
Welcome to electrical resistivity. Let's go over vocab before we start in all the math. We have resistance, resistivity, and conductivity. Resistance is dependent on three main criteria, which is the area, the length, and the material resistivity. We represents the resistance in a simple equation, noting that rho here, this rho, is actually the resistivity of the material. Now, do know that the resistance is what we are measuring, and we can measure it. Resistivity, we can't measure, but we can calculate. And we can rearrange this top equation, and noting that the resistivity is specifically the material's ability to let current flow through the material or block the flow of the material. Conductivity is just the inverse of the resistivity. We represent this by just writing the equation, and the conductivity is simply just the material's natural ability to let current flow through the material. Note that different materials do have different resistivities and conductivities. These three specific vocab words will be used throughout the rest of this. Now let's get into the math. So we're going to use this very specific law, which everyone in geophysics loves, which is Ohm's law. If we recall, V equals IR, where we have the voltage, the current, and the resistance. Let's draw a simple circuit. We'll have the voltage source, and then we have like this nice resistor. And we're going to say that the voltage is going to be 5 volts, and the current is then going to move through the system and go through this resistor, which we're going to say is 5 ohms. And the current will go up through and back around. So we'll just do this nice little loop. And we can put a voltmeter over the resistor to find the voltage change over the resistor. So we'll have this little voltmeter. And from there, we can then find the current, V over R, or we can say the change in V from the voltmeter. Now, say instead of like this simple circuit, we now have a circuit where we have these metal electrodes, which are just like metal rods stabbed into the ground. And they're connected through a wire that we have a known current source going in, 5 amps. We have now a connected system where the current will be traveling through here and coming up back here through the ground. But the current can basically go anywhere it wants, wherever it'll flow. So it can go either just straight across the ground, or it can have a nice little ray pattern, or it can go down and out and travel through the material in the ground. We can add more electrodes in the system. And we can say like they're all connected to this system where we then have voltmeters here, and a voltmeter here. And we can have different ray patterns from the current up here go through and go to more electrodes. The more electrodes we have, the greater spacing we have, the deeper in the earth we can image. So these all have a similar length. We're going to call this length L. We can get the change in voltage through our voltmeters up here. So we have I and we have B. We need resistance. So we'll recall that equation, rho L over A. The end result is we want this rho value. We want the resistivity of the ground. We can basically put these two equations together since we have a common factor of the resistance here and the resistance here. So we can rewrite both of those equations. We still want rho, so we'll solve for rho. So now we have the rho equation where we know the voltage, we know the current that we're pumping into the ground, and we also know the distance, and we know the area. In a more simplified version, to really understand this equation up here, we can represent this ground equation as a box where we have the material's rho value, we know its length, and we have the cross-sectional area. So this represented into a smaller form of this to find this resistance up here. So now we're going to look at different material resistivities. We use this in geophysics so we can about estimate what kind of material we're actually looking at through our resistivity survey. So if you look at this chart here, the farther over to the left it is, so all the way down over here, the more resistive it is. So for example, if we look at, so say like salt water is really conductive. Conductive being current loves to flow through it, and resistive being current doesn't really like to flow through it. If we look at like the clays and silts and shales and sandstones, that's kind of what Colorado soil is. So we're in between the resistive and conductive soils. Or if we look at, say, graphite is really conductive, which is up over here. Since this is a material chart, it doesn't have like air, for example. Air is incredibly resistive. So the only reason why we're not getting electrocuted from the outlets that we have just anywhere is because air is really resistive and the current of the outlet doesn't flow through it. Fun facts. When we take an electrical resistivity survey, we actually get these things called pseudosections. What a pseudosection is it's basically just telling us what the approximate apparent resistivity is. So we can equate that to the resistivity of the material underground. With this apparent resistivity photo over here, we can see that the bottom image, there is a really red portion right in the middle. This red section is a very resistive body, and that is a possible buried chamber, like it says in the photo. And depending on what we're looking at, we can possibly see, like, say, we can see water being very conductive. So that would be like a bluer body, depending on what our scale is. The color bar scale under here has blue being very conductive, red being very resistive. So it really depends on what color scale you're looking at for it to equate to like what resistivity or conductivity that you're looking at. And to seismic.
All right, let's talk about seismic. Seismic is basically like sending sound waves into the ground and listening for what comes back. And the way we do this is like dynamite, or what we're going to use is an accelerated wave drop, which is just a big heavy hammer. And these waves, which I'm sure you guys know about, are defined by something called velocity, a frequency, and a wavelength. And in seismic, we want to know all three of these parameters. So mechanical waves like compressional waves and shear waves propagate through a medium by something called acoustic impedance. Acoustic impedance is defined as AI or Z, or the velocity times the density of the medium. So that echo we heard back at the Grand Canyon is classified by something called a reflection coefficient, which is how loud that echo is coming back at you. So the reflection coefficient is your second impedance subtracted by your first impedance over the addition of the two impedances. So I've drawn a typical picture of what we call half space. We have air and then 3 layers of rocks in the lower half space. These have acoustic impedances, velocities, and densities of layer 1, layer 2, layer 3, and each have a height of h1 and h2. And here's where we get into the math. So if we transmit a sound wave, it's going to propagate down, and it's going to hit that boundary, and it's going to come back up. But some energy will still go through that second layer. So you send in a signal, and it's going to bounce back up at that interface. And the time it takes to come back, we can estimate the velocity and the thickness. So simple time equation, time is equal to your distance over a velocity. And in this case, distance is h1 and v1 for the velocity. So if we do this and we go along the surface, this is called vertical profiling. And we'll get an image of this boundary layer. And it might look something like this. Perhaps there's a little defect, maybe an incised channel is what we might call it, from a river. If we send down that signal and come back, that's going to come back at some time delta t. But if we have this channel, there's going to be some difference in time because it's got to propagate this distance And that's how we're going to image maybe a dip in the rock surface, because this time is going to be shorter than this time because this one has to travel longer and come back up. So what we just looked at was basically you listening to your own echo. You send out your own signal and listen back to that echo. So now let's say you have a friend and you're hiking down the Grand Canyon and you say, hey, wait up. They're going to hear, hey, wait up, and that's going to be a wave that travels along the surface and hits them directly. But there's going to be a second one. It's going to bounce off the canyon and hit them. So that's going to be something like this wave. It's going to propagate down and bounce back up. Now, just like before, we don't know how wide the canyon is, let's say. And you don't know how far your friend is in front of you. So you need to figure this out. And so you'll yell at time 0, and your friend will give you time 1 instead of you getting your own time 1. And through some simple geometry, we can calculate this. We have the wave coming in. It travels a distance x over 2 as you're looking down on the ground, but it really travels a distance d along its rate path, and it hits that interface at an angle, call it theta. We now use Pythagoras' theorem to calculate the distance that the ray has traveled just in this half section. Pythagorean's theorem tells us that the distance is equal to the square root of x on 2 squared plus h1 squared. Since the ray has now traveled a length d and then back up another length d, we can multiply by 2. Time is equal to distance over velocity. We can then take these two equations, do some jiggery-pokery, and then solve for the time. T is equal to the square root of x squared plus h1 on 4 squared all over, and in this case, v1. So now that equation tells us how long after you yell, your friend will hear you, or in this case, how long after you send a signal from your transmitter will the receiver hear it. And that's from this one that reflects here, not from the direct wave that travels along the surface. So say now you're sat down having lunch, but your friend is continuing down the canyon, and you want to see how far along that canyon they've gotten. So we can write this equation here as a function of distance here. We'll call that distance x. So I'll rewrite that equation for t as a function of distance is equal to the initial time you sent out your signal plus distance your friend is along the trail over twice the squared velocity times that initial time. And so this is the equation, the basic equation that we use in seismology. And this picture is a basic schematic, and it holds true for almost any situation you might see in seismology, which is great. So sometimes seismic isn't always the best tool to use, especially when you're looking at acid mine drainage. That acid in the soil is going to make that soil really conductive, which is why electrical resistivity tomography is going to be really useful. But since seismic is such a huge field in geophysics, and it was basically what started the field of geophysics, it's good to go over. So here's a couple examples of what seismic can be used in. A couple of these examples, like this one and this one, are used in oil and gas, and this was actually from my final project in a class I took. You can also use seismic on planets like this, and also to study earthquakes, which was a part of my undergraduate research. And here's a couple of photos of what the mantle looks like based on those shear waves propagating from an earthquake on the other side of the planet that came through the Earth and was recorded at the opposite end.
Hi guys, so you just learned about seismic, and now we're going to learn about GPR. What is GPR? GPR is ground penetrating radar. So like seismic, it uses waves, but instead of using waves like Kieran explained where it's like talking to someone, these uses light waves. So in a GPR survey, again, we're on the ground because it's all non-invasive, and we have a transmitter and a receiver, and both uses antennas. So the transmitter is going to emit a wave that's going to travel through our ground, and it is sensitive to electrical properties within the Earth. So it's going to sense whatever our body is and that's sensitive to, and it's going to reflect that signal up to our receiver. So in seismic, you learn that we are able to vary the distance between our transmitter and our receiver. But in GPR, we fixed that because it's going to be on a park, which you'll see on Friday. This is essentially going to let us do vertical profiling for our imaging method. So in construction, we can use ground-penetrating radar to go over the ground and sense any kind of sensitive materials like rebar, because rebar is going to be super conductive, so we'll be able to see that difference once we start imaging. As you guys will see, we're also going to be trying to find sprinkler lines, because the water is going to be more conductive than the rest of the surrounding area. So that is GPR.
So all of these different methods that you just learned about can be used to study many different things around the Earth and other planets, including hazards like earthquakes and landslides, different formations on other planets, the climate, so ices, the ocean, and then in our specific case study that we'll talk about in class on Monday, which will be about mining in Colorado. So we'll see you in class on Friday. Please make sure to wear closed-toed shoes, long pants, jackets if you need them, and hats because we may be out in the sun, and get ready to have some fun with some geophysical equipment.